Dr. Deepak, is there any chance of starting a research project using ISTE MBCET or ISTE Rachna, please.
Yes, sir. I'm starting. Good evening, everyone. ISTE MBCET is proud to launch our Tech Talk series, ISTEch, for all the tech heads out there. We are so glad to see you join us for your tech exploration journey as we are bringing expert speakers to cover some major topics in the tech universe for you. Today, ISTE MBCET, in collaboration with ASME MBCET, brings to you the first session of ISTEch Talk series. We are fortunate enough to have an eminent and experienced speaker, Dr. K Rajiv, to take us through the world of space science, research, and benefits. Dr. K Rajiv obtained PhD in physics from University of Kerala and joined Space Physics Laboratory Vikram Sarabhai Space Center in 1993. He was postdoctoral research physicist at University of California, San Diego, USA during 1998 to 1999. Currently, he is a director of Space Physics Laboratory, VSSC, and is a principal scientist of the National IGBP Nobel Project. He is the Indian representative to COSPAR Council and member of the Research Advisory Committees of the Indian Institute of Geomagnetism, Mumbai, Indian Institute of Tropical Meteorology, Pune, and National Atmospheric Research Laboratory, Tirupati. His areas of research include atmospheric aerosols, clouds, radiation, middle atmospheric dynamics, boundary layer physics, and satellite and lidar-based atmospheric remote sensing. He has published over 70 research papers in peer-reviewed international journals. 4 researchers obtained PhD under his guidance. ISRO and NASA Earth observatories release news items on his findings on aerosols, clouds, and radiative impact. So without any doubts, we can be sure that this session will be effective to its roots. Now, I invite the pillar of strength of our prestigious institution, Dr. Abraham T. Matthew, the principal of Mar Basilius College of Engineering and Technology, for the welcome speech. Sir, please.
Thank you, Rachna. Respected Dr. K Rajiv, my dear colleagues, Dr. Deepak G. Dilip, Ms. Soumya, Mr. Bobin Saji George, Dr. Nidhi MP, Dr. Shalu George, and all my dear students and other colleagues who are online. Good evening to all. I'm very glad and very honored to welcome our distinguished speaker, Dr. K. Rajiv. As you have seen in the biodata read by Rajna, his career is very illustrious and you can say very accomplished. And still, sir is working so quietly and so politely dealing with us and talking to us. This shows the eminence of his character, and that we appreciate very much. Sir, we are keen to listen to you, and we believe that you have a lot of things to share, and which will not be able to cover it in 1 hour, but we will keep interacting with you after this talk. And we also think to bring you and other scientists into a close network of experts so that our students can constantly interact with the eminent scientists of ISRO. And we would like to utilize the proximity of our college with VSSC campus so that our students can be benefited and our teachers also can be benefited out of that interaction. I am very glad to welcome you, sir, to this evening. I also welcome all my colleagues and my dear students to this session. I wish that this session lead to a fruitful discussion and our students and teachers will get enriched with the great knowledge that Dr. Rajeev can share with us. Sir, welcome. Thank you.
Thank you very much. It is an honor for me to be with you. What is our program now? Am I starting now, or is there any?
Yes, sir. You can start.
Yeah. So, respected principal, Dr. Abraham T. Matthew, respected teachers and students. Actually, it's truly an honor for me, when the principal himself comes and then welcomes. And I was also, thankful to Deepak sir, and also Rachana, Soumya madam, and Sri Vinayak, who was actually linking with me and initially proposing. I'm extremely thankful to all of you for inviting me to this. Probably I am an outsider to your community. The reason being, you're all engineers or budding engineers. I'm not an engineer by profession. I'm a scientist. I'm a physicist rather. My area of research is atmospheric and space physics. Of course, I will be able to tell you a little bit on, what exactly we have to do in space research and where you people also will be coming in link, because beyond a line, beyond a border, the things becomes interdisciplinary. There's no question of something like physics, chemistry, mechanical engineering, electrical engineering. I'll tell you a simple example. Atmosphere is a fluid, and in our area we have numerical modeling. Okay, modeling of the atmosphere. The best people is mechanical engineers in that aspect. My professor, University of California, San Diego, is an electrical engineer by profession. Of course, he is one of the most renowned atmospheric scientists in the world. And same is the case in India. You look at any big institutions, the true leaders, they don't have this kind of a strict boundary of mechanical, electrical, electronics. They will be rather having a core area of themselves. That is true, because you cannot be a master of all. But at the same time, things get spread out without having a close boundary. So now I'm thankful to you for inviting me to this. I will straight away go to my presentation. My entire screen, into screen select. Okay. Entire screen. Allow it. Are you able to see my screen?
Yes, sir. It has come up. It has come up very much.
So thank you. Then we will go ahead with the presentation. I have a lot of slides with me. I may rush at times, depending on the time that we have. What I want you to follow is there are certain catchy points there. There are certain points where I kept the slide just for the sake of it, that you will get impressed upon. Yeah, there are some very, very important. There are certain areas where we have to, spend a little bit time. So I may modulate it like that and then go fast in certain slides, but that is okay. At the end, we can have a discussion if it is required. I may take something like 45 minutes or maybe another 5 or 10 minutes, but you can stop me at any time, because if I overstep. So thank you. We will be going to the lecture on space science, research and benefits. Because why benefits? We are spending the common man's money. Okay, it should be for benefit. It should not be in the just for academic purpose alone. There has to be academic purpose. Definitely there has to be academic purpose, because firstly, fundamental or basic research eventually lead to industrial research or other applications. An application which we may find that absolutely no use now, you will find it that it is one of the most important things, maybe after a decade, maybe 2 decades, maybe several decades. That is the way it happens. So there is nothing called, basic research is not important. Basic research is the most important thing. But at the same time, we need to impress upon why exactly we are doing all these kind of things. Where is the, importance of that? Coming to the need for atmospheric and space research, reasons are plenty, but I have listed only a few. First and foremost is understanding the planet Earth, where we live, because it had a past, the past running into maybe millions, billions of years, the present, and there is a future. We have to know that, we have to assess it, we have to take remedial measures in case we are actually doing certain overstepping, like what is happening now, the climate change. The Sun-Earth relationship, we have to assess and predict. There is something beyond probably you may be aware of between the Sun and the Earth rather than just the radiation. We will come to that in a moment, which directly affects your day-to-day life. Planetary exploration, because planets actually have resources. We need to understand the fundamental physics, but then at the same time, they actually give you a picture of what was your future, past, and what could be your future. That also is there in planetary exploration. Astronomy, of course, the basic research on space environment and evolution, but that is also an area where the fundamental research advancements is closely linked to the the true evolution of our scientific fields. You name it, in any area. Coming to these are all, it may look like basic physics or basic research or fundamentals, but they are important for securing our space assets, because we know that we have space assets, and that is one of the most important thing currently. Having a better, leading to better improvement in our quality of life. utilizing the space environment for improved quality of life. And it also is a driver for new technologies, and there are several spin-offs that come from the space science in addition to the direct impact. The driver of new technologies, for example, microgravity experiments. There are certain things which you cannot do on the ground, you need space. There are national interests. There is economical and social benefits. In a moment, we will come to that. And there are far-reaching implications due to the longer lead time in space research. Okay. This is the Earthrise Apollo photograph. Such a beautiful planet, but it is so fragile. So fragile that actually we will understand in a few minutes that how fragile that it is, especially the environment, due to the human activities. The placement of Earth with respect to the sun compared to other planets is so important that govern the climate. There is, as you go away from the sun, the radiation from the sun. Sun is everything for us. Okay, the radiation comes from the sun. That is the one which is actually, sustaining life on Earth. Perhaps the breakfast, lunch, dinner that you have taken now today has come from the sun, basically from the sun. Okay, of course it was there was a transformation that was taking place on Earth, but basically the energy has come from the sun. And we are placed in such a perfect thing that water can exist in all three phases. That is what it is very important compared to the other planets. So our temperature is such that water can exist in all three phases. What is the importance of water? Water is a primary component for the existence of life that we all know. But what is more important also is it can transfer the energy from one place to another through evaporation, condensation. One simple example, a lot of energy from the sun falls on the equatorial region in the Earth. This energy is absorbed. Atmosphere, the surface will get heated up. In that process, actually, ocean water also will get evaporated. Ocean or soil moisture also get evaporated. Latent heat evaporation is taken from the surface. Then it is going to the atmosphere. It lifts up, gets into the atmosphere, upper altitudes. Clouds get formed because it condenses. See, latent heat is taken from the surface, went to the atmosphere, and dumped the heat there, like a perfect heat engine. Okay. Otherwise, this heat will not be transferred to the upper atmosphere. That is one. Two, it transfers laterally. For example, when you have the moisture that is taken up from here, it need not necessarily condense over, water vapor from Trivandrum need not condense, water from Trivandrum need not condense over Trivandrum. It may be laterally moving. Actually, we have global cells we call Hartley, Ferrel cell, polar cell. It can go up to very, very long distances, and that get condensed there. Means the energy that is taken from here is dumped not over Trivandrum, upper atmosphere, but rather at a very far off place. This is a very, very important criteria for any planet for water to exist. Of course, we also know that water is one of the primary constituents that we look for life, in addition to the carbon chain, that is the existence of carbon or organic material. This is an important thing for us. Sun emits radiation, we all know. Okay, radiation means, when I say radiation, namal the normal veil. Veil means the sunlight what you see. But actually, sun emits extreme ultraviolet radiation. Sun emits X-rays, and sun also emits radio waves, which we don't usually come across. But that is important for us, for the sustenance of our life itself. Not only radiation, sun emits particles. That is, for example, protons. They come at very high speed. The speed can be of the order of 300 to 1,200 kilometers per second. In 1 second, it will travel at a velocity of 300 kilometers to 1,200 kilometers. Such huge speed, you will not be able to stand. Okay, if we are exposed to such an environment, there will be catastrophe. But we have atmosphere. We have, what is more important is we have a magnetic field. Earth has a magnetic field. A charged particle cannot move across a magnetic field. Okay, there is a force called a Lorentzian force. You are aware of it, that will drift it along the magnetic field. Then Earth, actually in principle, Earth has a dipole, like a typical dipole magnetic field, you have a dipole. But then because of the solar wind interaction, it get compressed in one side and get elongated in the other side. That is what you are seeing. Okay, so these particles are not simply allowed to enter into, but not all of them. Some of them still penetrate, but they cannot penetrate through our region, equatorial region, that where we are living, but rather they penetrate through the magnetic field where the magnetic field converges in the North Pole and South Pole. So through the magnetic field line, they can come because the Lorentzian force is acting perpendicular to the magnetic field. All right. So if it is along the magnetic field, the force is zero. So the particle will not find any problem. It will simply come down. And you already know that this is what is happening. What is causing aurora, which is the the bright curtains of light that people record. People have observed over the polar region, which is very much there. But then it has also an implication. It can have huge damages in your electrical circuits and transformer circuits, electrical lines. And there are cases in Canada, US, or higher latitude places where these particles come down. They can change atmospheric conductivity and burn transformers or damage electrical lines. Such episodes have happened in the past. Not only that, these particles can damage our satellites. The satellite that you are going up, it can. Some of them are even beyond the magnetic field of Earth, the protecting magnetic field of Earth. They are exposed. So unless you have a protecting system, your satellite will not be able to withstand these kind of things. Of course, satellites has protective systems, but then there are episodes, we'll come in a moment, where these kind of things also can be overtaken. All right. Now, I told you that sun emits not only visible radiation or IR radiation, sun emits actually extreme ultraviolet, X-ray, gamma ray. This is what sun you can see in different wavelengths. The 1, 2, 3, these top 3, actually they belong to the X-ray to extreme ultraviolet. The 4 belong to ultraviolet. 5, 6 belong to the visible radiation. 7 infrared, near infrared. 8 far infrared. So when you look at the sun, the same day at the same time, you look at different wavelengths. Sun has different properties. Actually, sun emits huge. Sometimes there can be charged particles emitted in a lump sum. We call that coronal mass ejections, which can have sizes much more than that of Earth, which can damage the Earth itself. This is one such episode. There's a huge coronal mass ejection and Earth size is kept there. Such coronal mass ejections can come towards Earth and engulf Earth, which can actually have a completely different impact compared to normal time on Earth. And it is going to affect our satellite systems. There are records in the history where satellite systems were damaged by such things. Now we have protective measures for that. And that means we have to keep on monitoring what is the state of the sun. All right. We are going to have a mission from ISRO that's called Aditya L1. I'll come towards the end of it. We are going to monitor continuously the sun from a point that is called L1, where the gravity of Earth and gravity of sun are equal, so that the satellite will be continuously in the sun-Earth axis. We'll come to that in a moment to monitor these kind of episodes. I also told you that sun emits all kinds of radiations, but sun emits more or less like a black body. You already know black body, what black body is. Black body means, a body whose radiative spectrum looks like what is, defined by the Planck's distribution law. All right, the Planck's distribution law. This is what is expected for a temperature of around 6,000 Kelvin. This is the dashed line is what is expected from a black body. But you also have that. Most of the radiation is following that. But you have extreme ultraviolet, X-ray, and all those things that depart completely from that, and also on the farther side in the radio domain, where again it departs. Just from this graph, you can infer one thing. Sun has so many layers. There are interior layers which are having much higher temperature than the photosphere. All these inferences come from an observation. A radiometer sitting on Earth can actually probe inside the sun. That is the beauty of science. This picture, given to a radiation scientist, he can infer what is the internal structure of the sun to a reasonable extent. That is the beauty of science. You don't have to go there and then probe. Of course, these are only inferences which you can come. You need to have, of course, other kinds of measurements also. All right. Come to the planets. We have several planets. We have inner planet. We have outer planets. The Earth gives that pink line. What you are seeing. The y-axis. This is actually supposed to be altitude, but instead of altitude, what is plotted is pressure. Why I put this figure is because all these planets have molecules. They exert pressure. The pressure at the surface, we'll come to that after some time, is around 10 power 5 Newton per meter square. All other planets also have similar. Some are having much larger pressure at the surface. Some are having much lesser. All of them have a temperature. The temperature will vary with the height. For example, in the Earth case, temperature initially decreases, comes to and then slowly increases, then again decreases, then again increases. Whereas Venus, for example, it monotonically decreases for a much higher height and then it starts increasing. For all planets, one uniform thing is at higher altitudes, much higher altitude, temperature will be increasing drastically for most of the planets, except very few, like for example, Pluto kind of thing. Okay, but all other planets, which is very far away from the sun, that's why. Okay, but all other planets, you have the upper atmosphere temperature going up. You can see the temperature axis. It can go to 1000 Kelvin kind of thing. Okay, let us come to that again. Let us, because our time is limited, I don't want to wander from Earth to planet to the astronomy. And basically, I'm not an astronomer either. I'm an Earth atmospheric scientist and a space scientist. So I will limit rather more focused on to Earth and space science rather than going to astronomy. All right. Let us come to the Earth atmosphere. As I told you, Earth's atmosphere protects us in various ways. Highly energetic particle from the sun, that is called a solar wind. I told you that they travel at a velocity of 300 to 1200 kilometers per second. Atmosphere stop it. Actually, rather the magnetic field has a critical role in stopping it or deflecting it, rather. All right. There is another very important thing our atmosphere is doing. Millions of meteors enter in the atmosphere every day. Now, when we are talking over Mar-Baselius College of Engineering and Technology, in an hour, around 60 to 100 meteors might have come. But we don't see them every day because there are meteors which you are able to see visually. There are micrometeors, like microgram sized things, which you will not be able to see. But their impact is huge. They enter with a velocity of the order of 11 to 72 kilometers per second. They may be microgram sized particles, but they can pierce through. All right. Earth's atmosphere protected. Actually, they get ablated up in the atmosphere, around 80 to 100 kilometer altitude. Most of them get ablated. They form a long chain of ionization of the order of 25 kilometers, which you can track from the ground with a radar. That's the importance of electronics and electrical engineers come in there. We have radar systems at Tumba, which track that kind of a system. And why do we want to track? Actually, you can study the upper atmosphere with that. That produces a long trail of ionization of the order of 20 kilometers. If you can track it with a radar, the trail that is going to drift, with the wind, is going to tell you what exactly is the wind there, right? 80 to 100 kilometers up in the atmosphere, sitting on Earth, right? You may ask, why should I do that? I will come to that in a moment. Why should you do that? The third important aspect is extreme ultraviolet radiation, X-ray, gamma ray. All these things are, atmosphere protected. The ozone in the atmosphere. The ultraviolet radiation is getting absorbed there, and then the radiation doesn't much penetrate it too, so that we have a proper sustenance of life the way we are today. Otherwise, you cannot withstand X-ray, you cannot withstand extreme ultraviolet. There are a lot of damaging effects to your biological cells, and we will not be able to live here. Of course, we also know that we are actually creating problem by destroying ozone. I'll come to that. This is Aurora. You already have seen the charged particles coming and then precipitating through the polar region where the magnetic fields come down. All right, converge. That is Aurora. The upper atmosphere has a layer called ionosphere. I told you extreme ultraviolet radiation coming from the sun, atmosphere absorbs. Actually, rather that radiation is absorbed, and that is used to ionize the atmosphere. Like a charged particles will be emitted from an atom by absorbing that radiation. Then the upper atmosphere will get ionized. So there is an ionized layer in the upper atmosphere. Electronics engineers, in the beginning, used this as a major communication network, a facility for that. you could, transfer the radiation, the transfer communication across the Atlantic, because you had a layer there at 80 to 100 kilometer that was produced by the extreme ultraviolet radiation. But that is one aspect of it. The second aspect is when you are communicating with the satellite, you have communication systems, your telephones, your mobile phones and things like that. The ionosphere can affect it. So you have to select your frequencies in such a way that the ionospheric effect is not there much. It will pierce through the ionosphere. There's a very, very important aspect other than this. We all use GPS systems. Without GPS system, I don't think you can go anywhere these days today, because you put in your Google map and Google tell you where exactly you are going to and which is your location. How is it possible? There are GPS systems, or we have IRNSS systems for India, multiple satellites. They, based on a technique called a triangulation, they exactly give you, and triangulation plus there's a time factor that is coming in. They exactly tell you where is your location, right? How? The radiation that is passing through the atmosphere takes definitive amount of time. You can calculate it exactly. There's a small problem. You assume the refractive index of the atmosphere for that. And refractive index of the atmosphere, you can assume safely to a reasonable accuracy, except for ionization changes it minuscule. Small change in ionization. A refractive index can be caused by this ionosphere. Not only ionosphere, water vapor in the atmosphere. If you don't model it properly, you can be in error by of the order of hundreds of meters. Okay, fine. When you are driving, you can ask at least somebody, okay, if you are nearby hundreds of meters, that is still fine. But there is another thing. The aircrafts. Now, earlier, that aircrafts get navigated, by the pilot only. But there are new aircrafts coming up, new navigation systems coming up, which will be in autopilot. Autopilot in the sense, even while, to a reasonable extent, even while landing and taking off. While landing, imagine a situation when the aircraft is coming down and it estimates the height of the order of a few meters even, right? By a few tens of meters, a few meters, it is going to be catastrophic and your aircraft is going to be broken. It is not possible, which means you have to study the ionosphere, you have to model it, and you have to predict it. And you have to estimate the GPS information or the IRNSS information of ISRO. You have to have a calculation for this. We do that. At my laboratory, we have made a space physics laboratory of Vikram Sarabhai Space Center. We have made algorithm to correct it. How do we make it? We first explore ionosphere. How long? We are studying it for decades, and we know very reasonably what exactly the characteristics of the atmosphere. Is it all done? No, there are several unknowns. Still, we do not know certain things. There are certain limitations. Okay, we'll come to that. So, space weather impact. The state of the sun will affect your ionosphere, I told you. That will change your global positioning system, your navigation, disruption of electric power transmission at high latitudes. It will affect satellite communication, and all the more, it will affect satellite safety and drag, because it can drag the satellite, right? So space weather is going to be one of the major impacts in the coming years because of our dependence on the satellite systems and communication systems, the way I presented it, right? There is something called vertical coupling of the atmosphere through waves. Mechanical engineers will be aware of this. You have ripples, for example, formed in water. You can call it as a wave. That ripple is produced by dropping a stone, for example, that produces a temporary void in the surface, which produces a pressure gradient, and then ripples get formed because the molecule, the water from the surroundings come and fill it. But while coming and filling it, they all rush towards that. They come and then accumulate. That accumulation is also not possible for water. They just go down. This kind of an oscillation will be keep on doing, like something like a simple harmonic, simple pendulum, right? Very similar way, you can have atmospheric waves. There are waves in the atmosphere of various, spectrum periodicities, which can transfer the energy from the surface to up in the atmosphere, including up to the ionosphere. Okay, so all these things, if you want to really study the atmosphere and predict, you have to know what is the state of the atmosphere, not only from here up to the ionospheric thing. I'll tell you another example. When rockets are launched or spacecrafts are re-entering, you need the model of the atmosphere. The spacecrafts are designed for what is the drag that is introduced by the atmosphere, What is the deflection in the orbit that can be caused by all these things? A simple example to that is, the Challenger disaster. The Challenger disaster, when the Challenger was entering back, there's a place where, the Earth's resistance get exponentially increased as it comes down. So around, say, 150 kilometers down, there is a huge resistance that will be built up that will heat the spacecraft, and unless you have a proper heat shield, things will be damaging. Things will be damaging means there can be catastrophe. That exactly is what happened in Challenger, where a tile misbehaved. There was a problem with the tile, just a small tile. That the whole Challenger disaster happened at this kind of region. So you have to have a proper understanding of the atmosphere if you want to have a proper launching or re-entry of a system. So that's why I'm telling all these things are highly coupled systems. All right. So this we have already discussed. I will not go further again. The impact of weather or ionosphere on global positioning system, aircraft navigation, and we already have at ISRO, we have taken up the task of ionospheric and atmospheric correction of GPS signals for our region. Okay. Coming to the neutral atmosphere, the way we are is because of the nitrogen and oxygen. That is what we would think, because around 99% of the atmosphere is comprising of nitrogen and oxygen. But the fact is, there's a major role for all minor constituents, especially carbon dioxide, water vapor, ozone, and things like that. There are a lot of other species also. You know the effect of water. You know very well the effect of carbon dioxide. That is a greenhouse gas. Of course, water is also. And the concentration of ozone is what is given there. Other species is given there in percentage, in bracket. For example, 99% is nitrogen, oxygen, and around 1% is argon. There is only much less than 1% is by water, carbon, much less than 1% is carbon dioxide, much less than 1% is ozone. But they are the ones which actually have a pivotal role in regulating our life. I just want to impress upon you how the atmosphere of Earth behaves or look like. There's atmospheric pressure decreases exponentially with height. The pressure is the weight of the air column above you. That is pressure, because pressure is something, the force acting normally. Why there is a pressure? Because atmosphere has mass. The mass pulled by the Earth due to gravity gives it weight. This weight is what we call force. And force acting on unit area is pressure. So the total mass of atmosphere, if you calculate, the total mass is of the order of 5 into 10 power 18 kilograms. Compared to the atmosphere, Earth, it is 10 power 6 times lower. Right? The pressure that it exerts on the Earth's surface is, I told you, 10 power 5 Pascal. That is 1 Newton per meter square is 1 Pascal. Right? I did a small calculation to insist upon, you can do this by yourself. I told you the Earth's surface pressure is close to 10 power 5 Pascal. That is 10 power 5 Newton per meter square. You just consider your cross section. You have a head, you have a shoulder, you have a body. You just take your cross section and then multiply by the pressure. You will get the total force that is acting on you. And if you divide by the gravity of Earth, you will know how much is the air that is above you. If you calculate over an average person, around 400 kilograms of air you are holding in your head and your shoulder. Each one of us. Our own weight is probably, of the order of maybe 10 or 20% of this. How are we able to do it? Actually, you don't hold anything. There's another force that is called pressure gradient force, because air is a fluid. It will be pulled down by gravity, but air molecules also want to go from a high pressure to a low pressure. So as the pressure, with altitude, pressure will decrease, but molecules will be pulled down. There's an equilibrium between the vertical pressure gradient, that is, it wants to go from a high pressure to low pressure. Low pressure is in the upper altitude. There's a competition with the gravity which want to pull it down. So it is something like a floating situation. That's why you don't really face this 408 kilogram, but indeed 408 kilogram, 400 kilogram of air is above you and me. We are holding it. Of course, only as I told you, the pressure gradient force balances the gravity. So it is something like a floating scenario as far as the air is concerned. Around 50% of the air mass is below around 5 kilometers. 50% of the atmosphere is below around 5 kilometers. And around 90% is below around 10 kilometers or maybe around 9 kilometers. And around 99% is below around 18 kilometers. Around 99% of the atmosphere is below around, around 28, 18, 19 kilometers. 99.999% is around less than 30 kilometers. So why I told all these things? Where is the limit of atmosphere? Where do your space start? I was telling you that I am going to talk to you about space. Actually, your space starts right from the surface of Earth upward. And if you want to find an upper boundary for Earth, it will be very, very difficult for you. Even after 10,000 kilometers, you will find atmospheric molecules. But of course, the pressure will be extremely small. But they will be important. Those molecules are sufficient to drag the satellite. And finally, the satellite will fall back. Right? Otherwise, if without any drag, satellite will be continuously going. mv square by r is equal to gm1 by r square. Right? This is the equation. So it will be continuously going around. Unless there is another force that is acting on it. That force can be dragging. Even at 1,000 kilometers, even at 10,000 kilometers, there can be drag. So it is very difficult to find where is your upper boundary. So that comes, where is the boundary of the influence of Earth. Of course, if you are talking about several hundreds of Earth radii, then of course you can say that, okay, Earth's influence is not there. Okay, we'll come to it. You already know that, the solar radiation that is coming in, and we have the Earth emitted radiation that is going out. This solar radiation coming in will heat you. The emitted radiation will be cooling you. But then there is a problem. The emitted radiation by the Earth is not going all back to space, but rather there is some wavelength band around, of the order of around 10 to 15 micrometer, where you have the absorption taking place, absorption of that radiation. So the radiation that is emitted from the Earth will not go, but rather it will be absorbed by the atmosphere, which will re-emit, partly to space and partly back to you. Again, you got back more radiation than what you got. What you would have got otherwise from the sun. This is called greenhouse effect. And the perfect placement of that atmospheric window, there is a region over which the radiation will be going unattenuated. There is a region over which it will be attenuated. Attenuated means absorbed. That window is perfectly placed such that you have the kind of environment that is available now. That window is perfectly placed by whom? Primarily by carbon dioxide and water vapor. Of course, to a limited extent by ozone. See, that minor constituent in the atmosphere, which did not even comprise of 0.001% of the atmosphere, is the one which regulate your temperature. In the absence of that, the global mean temperature would have been around 33 degrees centigrade lower, and water would not have been in, vapor phase. Result is, you will not be able to, it will be all chilling, cool, ice kind of planet. This is called the greenhouse effect. I will not again go into the details. There's something called the climate change. So in climate change, what does it mean? Some amount of radiation comes in, some amount of radiation goes back, some amount of radiation gets absorbed at the surface within the atmosphere, and then there's an equilibrium state. This is in a nutshell. This is one of the most classical graphs I have ever seen, but I will not go much into the details due to lack of time. This itself will take around an hour. But the gist of the thing is this. The radiation that is coming from the sun and what is going back from the Earth are not balanced at the surface. They are also not balanced at the atmosphere. They are balanced only at the top of atmosphere. So within the surface and within the atmosphere, they are not balanced. Earth emits more than what it receives. Earth absorbs more than what it has received, and atmosphere emits more than what it has, emitted. Result is there's a non-equilibrium between them. How that energy is transferred? No, energy will be continuously accumulated at the surface because it has emitted less. Going back is less and absorbing is more. It is not happening. What is happening there? What is happening is, instead of through radiation, it is transferred through mechanical processes. That is the sensible heat flux, latent heat flux, same as your heat engine. Okay, that energy is transferred to the atmosphere, which drives the circulation from the pole to the from the equator to the pole, and that drives. While doing that, there is a problem. Earth rotates, so there's a force called the Coriolis Force, which is a fictitious force that will not allow it to go to North Pole. It wants to go to North Pole and it wants to go to South Pole from the equatorial region. It will not be allowed to do that. Instead, By the time it reaches the subtropical regions, it gets deflected and there it will sink. And sinking air will not cause any weather. That means it cannot cause your clouds and things like that. That's why all the deserts in the world are located in these regions. Whereas maximum precipitation, rainfall happens in the tropics, and of course at the subpolar region there is another cell, right? And this is the real dynamics of Earth. The atmosphere really in motion. This is obtained by stitching the satellite imageries all over the globe together, right? This is what the our prevailing climate, if you want to say, but the climate is changing. The climate is changing through natural processes and through anthropogenic processes. Anthropogenic means processes that are induced by the human beings. Natural processes include the Milankovitch cycle. I will come in a moment. The anthropogenic process you already know. Each one of you are emitting carbon dioxide. The bike that you are riding today, the carbon dioxide that has gone from there is going to be there in the atmosphere for next 30 to 60 to 100 years up to. Even after you leave this place, the carbon dioxide that was emitted by you today while coming to college will be there in the atmosphere. At the same time, we cannot say that we cannot emit carbon dioxide or things like that because we require energy the way we are living now. Even otherwise, we require energy, for example, for cooking. So there is certain amount of carbon dioxide that will be keep on getting into the atmosphere. But atmosphere has a natural way of removing it also. For example, through the through rain, part of carbon dioxide will be coming down as carbonic acid. That's why people who measure the rainwater knows it is actually acidic. In reality itself, it is slightly acidic. It will be more acidic if you put more pollutants. Okay, that's a different story. You also have a lot of aerosols. The amount of dust that you are putting in the atmosphere, the pollutants, the smoke, they are also going to affect the atmosphere, right? Geomorphology, because you are changing the albedo, you are doing deforestation, you are changing the surface characteristics, you are changing the water cycle. All these things are anthropogenic effects. When I told you about the gas emission, I told only one example of gas emission is carbon dioxide. You are emitting much, much dirtier gases through our usages of systems. For example, chlorofluorocarbons, which now it is stopped. Okay, which is stopped because of the effort by a few scientists who predicted it before the real effects started, but nobody believed them. I'll come to that. But is that all the natural processes that change the climate? No, it is. Anthropogenic forces? No, there is a natural process. The natural process is called Milankovitch cycle. There are 3 periodicities over which it will change. Earth goes around the sun in an elliptical orbit. But the eccentricity of the orbit is not constant. It will keep on changing. It changes over a period of 1 lakh years. It goes, reduces, shrinks, expands. That is, eccentricity increases and decreases with a periodicity of the order of 1 lakh years. That 23.5 degrees is our current tilt of the equatorial plane with respect to the Euclidean. The axis of the rotation of Earth with respect to the Euclidean plane. Actually, it is not 23.5. It changes from 21.5 to 24.5, which itself will change the amount of radiation that is coming and intersecting with the Earth at different latitudes. That changes with a periodicity of 41,000 years. There's another thing, this 23.5 degree, yes, 23.5 degree, that itself can be, 23.5 degree can be inclined in any direction with respect to the normal. That's called the precession of the orbit, which again causes something like 19,000 to 24,000 years. That also vary, like a spherical top. So you see, naturally itself, you are doing a lot of, the orbit of Earth, Sun itself will cause, climate change. But you remember the periodicity is thousands of years to lakhs of years. Okay, but what we are doing the climate change in the last 150 to 30 years. We'll come to that. How do you know that all these things are happening? These are all just, just like that people are conjecturing? No, there is evidence. There is evidence for the history of Earth. There is core, ice core. If you drill in the ice core regions, you will be each meter that you are, each centimeter you are going down, actually you are going back in space, back in time, of the order of, 10 year, 50 year, 100 year, 1000 year, 1 million year, 10 million year, life of that order. A visual example I'll tell you. For that, you don't have to go to millions of years. Trees, for example, annular ring of the tree. If you cut a tree, there is a ring that is formed around its core. That annular ring width is changing depending on the climate that is prevailing there. If you can calibrate it, you will have an idea about what is the kind of climate that prevailed. There will be a lot of trees flourishing and all those kind of things. With water, with the rain, it will be drawn to lakes, ponds, or oceans. Each year it will form a sediment. That itself will tell you what exactly is the kind of profile that existed there. What is happening in the past if you do the analysis properly. This is called paleoclimatology. I will not go again into the details, but nature records what it has been over the past thousands or millions of years. The question is, can you read it? You can. There are, science has advanced to such an extent. What is happening now? The climate is changing. I told you, carbon dioxide emission. See, there's a laboratory called Mauna Loa Laboratory on, in Hawaii, which is pristine, which is away from all pollutant sources. So it will give you a natural variation over the natural variation sense, not like a over a smoky region, but rather mixed over the whole globe. What is the carbon dioxide concentration? It changes from around 310 in 1960 to close to around 400. It has crossed actually over Trivandrum. We monitored. It has crossed over around 410 to 420 today. That is the kind of level that we have. You see how much? More than 100, 120 parts per million has increased, whereas its mean value was around 300. So 1/3 has increased. Obviously, temperature will go. And this is the climate change over our region. Those who are interested, there's a very interesting thing. There are two things which you can look at, those who are interested. One is called Ipcc, Intergovernmental Panel for Climate Change. This is a world body which assesses, based on the scientific studies, what is the kind of climate impact that is going to be, and what is the kind of effect that it is going to produce. Over India, there is another assessment that was made, assessment of climate change over Indian region by Krishnan et al. 2020. This, if you Google on Earth, you will get it. All right. But this shows that the carbon dioxide over Indian region is increasing like this. All right. But carbon dioxide amount was even increasing or decreasing naturally over millions of years. This axis, this shows how much it was changing over thousands of years before. 800,000 years before. 700 x-axis shows the time. 0 means now. All right. You are going back 100,000 years, 200,000 years, 800,000. What I'm trying to tell you is 8 lakh years before onwards, the scale is coming up. All right. It is showing. There is periodic change in carbon dioxide, but never in the history it has exceeded close to around 300. Now what is happening? You see the near zero. What is happening? Where I have encircled it. Just so rapidly it is increasing from around 270 to now today's value. I told you around it has crossed to 400 over last 100 years. And this is going to happen. This is going to cause catastrophes for the environment, which has been assessed. I will come to that. There is one more parameter that will be affecting, not one, there are several more, but one of the parameters is the albedo. You can see the surface albedo. Surface albedo you are perturbing. There is another very important thing is air pollution. There are a lot of aerosols which are suspended in the air. Aerosol means suspended particles in the air, which can be natural like dust or sea salt. There is large amount of dust that we emit, our transport system emit, industries emit, biomass burning emits, forest fire. So there are natural processes, dust, volcanic eruption, forest fires, and anthropogenic process, that is you and me, biomass burning, industrial emission, oil fires, all these things are dumped in the atmosphere. They reside in the atmosphere again, affecting the amount of radiation that is coming to us, which will cause another impact in the atmosphere, causing climate change. Another important factor is ozone. We were releasing chlorofluorocarbons and they were destroying the ozone in the atmosphere. The ozone is a protecting layer for us. The entire ozone, if you reduce to you bring it to the surface, the entire ozone in the atmosphere, if you bring it to the surface, the total thickness will be only 3 millimeters. You understand what I'm saying? The entire ozone in the atmosphere up to around maybe 80, 100 kilometers, you bring only the ozone, not other species. Bring it to the earth where your pressure is, I told you, 1,000 hectopascal, that is 10 power 5 Newton per meter square. At the surface, the thickness of the ozone is only 3 millimeters. And that is the one which protects life on Earth. This 3 millimeter will be changing a little bit, okay? It can go to 4 millimeter, it can come to 3 millimeter. Which are the species mainly? Chlorofluorocarbons. What is their lifetime? 100 years, 50 years. This is the lifetime of chlorofluorocarbons in the atmosphere. That means the chlorofluorocarbon which you liberated today is going to be there for hundreds of years, and it is going to destroy ozone. The ozone destruction is through, this is an interesting chemistry. Initially, these chlorofluorocarbons were thought to be wonder gases. It will not react with anything in the ground. But when it goes up, ultraviolet radiation from the sun can split, and the chlorine can come out of it. And once chlorine comes, chlorine will react with O3, it will form ClO plus O2. And ClO will react with another O3, it will form chlorine plus 2O2. The net result is 2 ozone molecules became 3 oxygen molecules, and chlorine went out unhurt to destroy the next one. A statistic says the one chlorofluorocarbon can destroy 10,000 ozone molecules before it is removed from the atmosphere. And it forms ozone hole. Ozone hole means there is nothing called a hole, but a region where ozone is largely depleted. This is an Antarctic ozone hole that is shown, that was formed in September 2020. You can see the aerial extent of the blue, and where the South Pole is there. And where the science comes to the rescue of us, your life, your existence is relying on a few people who predicted the importance of ozone before the ozone could get destroyed fully. They predicted that the wonder gas that you are emitting, if it goes to the upper atmosphere, it will be emitting chlorine, it will destroy ozone, and then it will go to a place where point of no return, because their lifetime is hundreds of years. People did not believe it. You know why people did not believe it? There's huge industries, the chlorofluorocarbon making industry, for example, air conditioning, one typical example. There's so many refrigeration, so many people are using it. If they are, asked to change the gas, it costs trillions of dollars of worth economical changes. Who will, they will be running in losses. So there's a huge, risk that these 3 scientists took, and they were awarded Nobel Prize. They took that risk, facing the scientific, proving the science, but facing the, the community outside who are not ready to accept it because of the economical changes. And this is an example of the model that they did, subsequent research. There's something called the Montreal Protocol. Finally, people realized that, ozone will destroy, because now ozone hole appeared. They told it before ozone hole appeared, but people did not believe it. Then first ozone hole itself, people got, gone. Now everybody joined together. Montreal Protocol, Kyoto Protocol, emission protocols. We are now, the global nations are coming together. Actually, this scenario shows 2 things. One, with the Montreal Protocol, means there has to be a reduction in chlorofluorocarbon, or you should not use it. That kind of a scenario. Vis-a-vis, if we were continuously using chlorofluorocarbon, that is on the right side. On the left side, what is shown is, with the Montreal Protocol, this is the way today it is. Like in the equatorial region, we have close to around 280. The polar region, you have higher values, but that is because of atmospheric dynamics. That's a natural process. But if we were not heeding to those 3 scientists or the subsequent actions by a wide community, by now we would have reduced the ozone much lower. And this is an example of, in 2060, 64, what would have happened? The entire globe would have been filled with less than 100 Dobson unit of ozone, which is life the way we see cannot exist. That is why I'm telling you and me owe a lot to those scientists who predicted these kind of thing, whom you will never remember, right? Valina, Paul Crutzen, and Sherwood. All right. We know that because of all our impact, and also natural processes, the temperature is increasing. Global mean temperature is increasing. Currently, during the last 100 years, the temperature over the entire globe, if you take, has increased by around 1 degree centigrade. But it is not uniform over the entire globe. It has changed by around 1 degree centigrade over the entire globe so far. It is not uniform. Now, there is no point in telling it has changed. Now, what is going to happen in future? So you need to have proper atmospheric models, fluid dynamical models. I'm telling you, the mechanical engineers play a very pivotal role here in the atmospheric modeling, fluid mechanics, right? And there's enormous scope for people in this area. Where they predicted, now different emission scenarios. You will continue to emit like this, what you are doing now, or you will cut down. So depending on the scenario, they predicted in the next 100 years what is going to happen. All over the entire world, it is bound to, that is a top figure, temperature is bound to increase. By how much? Maybe of the order of 1 to 2. If you cut down all your emissions now, even if you cut down, it will increase. If you continue to emit the way you are doing now, it is going to increase much drastic. That is, the change can be of the order of 5 to 6 degrees centigrade. And imagine 5 to 6 degrees centigrade, say, for example, over Himalaya, the entire ice is going to melt. The polar region, ice will be melting in no time. Sea level will be rising. All right. The precipitation, the rainfall pattern will change. Your monsoon will change. By how much? If you are continuously emitting the way you are doing now, the global average surface temperature can change by of the order of 4 degrees centigrade. Of course, it has large uncertainty in the estimate. It is not that 4.00. It is not that accurate. There's large uncertainty of the order of maybe 1 or 2 degrees centigrade. But it is bound to happen in the next 100 years. If not, suppose you are reducing all your emission scenarios, completely, then still it will increase, but the increase can be reduced to something like maybe a Kelvin. All right. But what is going to happen to the sea level? The sea level is going to continuously rise. The sea level will rise. Already it has risen, for your information. It has risen over the entire globe by of the order of around 17 to around 20 centimeter. It is further going to increase, and the sea level may increase by around 80 centimeters if it is continuously emitted. If not, the sea level will still increase by of the order of around 40 centimeters. And imagine 40 centimeters sea level increase. The civilizations are built all around the coastal areas. And you already know there are several cities in the world, several islands in the world which will be submerging if this kind of scenario goes. All right? And that is going to happen. Civilizations are going to shift in the next 100 years. Over India, what is going to happen? Over India, there's a separate assessment made by the Indian team. This report is worth looking at, Krishna et al. Where I will, due to lack of time, I will tell you in a gist. You emit realistically you reduce your emission. Still, the temperature is going to increase over India by around 1.6 degrees centigrade. If you don't do that, if you continuously emit the way you are doing, it is going to increase by around 2.7 degrees centigrade. I mean, I beg your pardon. This is over the tropical oceans. Over the Indian region, if you are continuously emitting the way you are, the temperature is going to increase by 4.4 degrees centigrade. This is an average temperature. Okay, it will vary spatially, temporally, and there is an uncertainty also, the order of maybe 1 or 2 degrees centigrade. If you stop the emissions to a reasonable extent, it is still going to increase, but that increase can be limited to around 2.7 degrees centigrade at surface temperature. And is it going to be uniform over India? No, it is going to be different. It is going to be spatially varying because the geomorphology also play a role, the emissions play a role, the response to the system play a role. In any case, your global mean temperature, your Indian temperature is going to increase, as we have already discussed. This shows how the time evolution of that increase will be. What is the cost? Government of India has already taken mitigatory things based on the forecast that were given, and government has decided that we will reduce the greenhouse emissions up to 35% of the current by 2030. You know what is the implication? The implication in cost economy is $2.5 trillion by up to 2030. Or probably around 15 years. This is what the kind of economical impact that it is going to have. But if we don't do it, we are going to be in farther problem. And this is not only with us, all global nations. That is why you are hearing, Kyoto Protocol, UNFCCC. There are several keywords you will be hearing. UNFCCC, Kyoto Protocol, Montreal Protocol, Paris Protocol, all these kind of things. Some of the developed worlds will not sign it because of strategy. Because the tropical, some of the regions in the higher latitudes, if they warm, it's not as bad as the current scenario. Of course, globally there will be problem, but they will have an upper hand still. So they want to bargain upon that. So we need to have highly accurate systems for regular and systematic monitoring of the Earth atmosphere system globally. Comes space assets. We need to map it for our natural resources, agriculture safety, and food security. And we have to have proper resource managements, meteorological forecasts, cyclones, disaster management, planning, pollution monitoring, cross-border trading. There's something called emission trading. All right. You are supposed to, you means India, will be paying tax if we emit more than what is allowed to us. And another nation also, same thing. So if you emit more, you are going to pay more taxes by government of India. That's called emission trading. It will affect the national security. It will affect our civilization. It will affect satellite safety. So many things will happen. So we have the monitoring systems at ground, with the balloon, and in space. For example, this is a network observatory which our laboratory, SpaceX laboratory, is running over the globe. Over India, we have a network of observatories. Over 40 places, we have the network. Over Antarctica and Arctic, we have our observatories. Over Himalaya, we have our observatories. And the Vikram Sarabhai Space Center has developed a radio zone day for balloon probe. With a balloon, send it in a balloon. This is developed by electronics engineers. What you have is a thermal system. A thermistor, a humidograph. That is basically capacitance measuring thing, and the GPS, which will give you the location. From that, you can change derive the wind. Balloon will be drifting with the wind. So if you know the location, you can derive the wind. All right. This is done by electronics engineers in VSSC. Okay? It's called Pisharati Sonde. It can be flown in a balloon. You can derive the meteorological parameters. This is being used in India regularly. And India has very, very major research facilities. This is a facility in Hyderabad. It's called High Altitude Balloon Facility, which can lift 1 ton of payload up to 40 kilometers. It's one of the rarest facilities in the world. Okay, 1 ton of material, 1 ton of payload can be lifted to 40 kilometers by this balloon. Okay, it's huge facility. With which we have utilized it to monitor, the black carbon emission by the species and to what extent it goes up in the atmosphere. We are also able to assess how much is the effect of aviation, the aircrafts in producing this aerosol, black carbon. That will have an atmospheric impact. We have a network of observatories, I told you. When we combine it with satellite, you will be able to derive, the climate change parameters as well as aerosols. One of the examples that is shown here is over the last 20, 30 years, what is happening to the aerosols over India? There is a constant increase in aerosol emission. This is what it is, based on the network observatories which we are doing. The instrument is a very simple instrument. It's called Radiometer. Again, a combination of physicists and electronics engineers coming together with physical principles from the scientists and electronics making the hardware. We have a network covering the entire India. Of course, we have to monitor from the space. We have the INSAT 3D kind of satellites, which will be making visible band observation. But there's a problem with the visible band. You will not be able to monitor 100% of the time. Nighttime, you will not be able to monitor anything. For that, you require another wavelength that is in the infrared. So infrared, Earth will be emitting, Earth or clouds will be emitting. You'll be able to get, it is something like a night vision camera. You can, observe the atmosphere or the weather continuously. We have another satellite which we did with the Indo-French payload. India and France came together for the radiation balance of the Earth atmosphere. This shows the global effect of cloud over the entire globe. This was done by my PhD student, based on the Mecca tropics, which was Indo-French payload. When we are doing active remote sensing based on a radar that is in space, we were able to derive a whole kind of scenario in cloudiness over the Indian region. This is done by another of my PhD student. He was awarded PhD. And you see there's a whole kind of thing in terms of cloud occurrence. This is the first time that was a discovery kind of thing. Otherwise, with the spaceborne systems, it was not able to discover. With the radar only, we could do that. And we have, scatterometer in the space, which will be deriving the surface winds over the entire globe. Otherwise, over the ocean, okay? Otherwise, you will not be able to derive, over the open ocean. Who will measure? Only ship, once in a while going, only will be able to do. But you can measure continuously, okay? India is doing this. And of course, this is being used by the world also. By even NASA is using, our SCATSAT data. And this is another example of SCATSAT data or surface wind. Why should you do that? Cyclone formation over any place in the globe can be monitored with this, because it first gets triggered at the surface, and then you can track it, predict it, you can save life. You can also, monitor the ice over the Himalayas or over the polar regions based on the system. Another important aspect of spaceborne observation, which you may not think, is night light. This shows the night light. Why should you do this? Agencies all around the world is looking at the other neighbor on the development that is happening, the energy consumption. The kind of impact that this kind of a graph will have under time evolution. It is enormous. Otherwise, how do they assess globally? There are various mechanisms by which they will be able to assess what is happening in India, what is happening at other places, based on this kind of remote sensing. Night light will give you a progress that is being made by a country. If you make the night light, estimation for this year compared to last year, you will know how much we have progressed in terms of our developments, infrastructure. This is an example of, India building, India-Pakistan border. We have built the, built and lighted the border. And that is what is shown from the ground. This is a photograph. And when, you look from the space, it looked like that red line. And that was progressing. Actually, if you play like a movie, it was something like it was moving like this, because it was getting built up and completed. Forest fires. All over the world, you have tremendous amount of forest fires happening, biomass burning happening. We can assess with satellite. Global lightning. Not just a globe alone. Your own location you can do, and then you can cover the entire globe with satellites. We have systems for that. Global sea surface temperature, which is actually primarily required for climate studies. Soil moisture, which is required for the agriculture purpose. Our farmers require this. Actually, the models are taking this as a primary input, soil moisture. We can do that. And these are all for the weather kind of thing. And for the ionosphere, we have systems. We have radars for the ionospheric studies at Tumba. And of course, we have all around the globe also, other laboratories. We have rocket-borne payloads, all made by electronics engineers in conjunction, working together with physicists. All right. We have the, payloads for satellite, for rocket, and we have ground-based radar systems. This shows an example of the ground-based radar system that we have in Tumba, okay, with which we were studying the ionosphere. And this was, initial system was established way back in the 70s. We had classic electronics engineers doing the job, right? And this is another example of, an Indian MST radar facility. This is the biggest radar facility in the world. There are two. One is Mu radar. Second is this radar system. Of course, there is another that is in Jikamarka. These are the biggest radar systems in the world, which can, you see, this is a field. This is in Gadangi. This is called the National Atmosphere Research Laboratory of Indian Space Research Organization, Department of Space. This can monitor continuously the atmosphere, the temperature up to around 20 kilometers, right? And then in the upper atmosphere, ionosphere, continuously. We have the IRNSS navigation satellite, like GPS equivalent over our region, Indian region, which is already working. It is called Gagan. And Navik, it is renamed as Navik now, IRNSS satellite. There you require, as I told in the beginning, atmospheric and ionospheric correction. We do that. And this is the navigation technique. I will not go into the details due to lack of time. And we have another mission that is coming up. It is Aditya L1. I told you right in the beginning, solar wind is affecting our space weather, our ionosphere, the propagation delay, the GPS monitoring, the satellite assets. So we need to monitor that. There's a system that we are flying, which will be going probably in a year or two. I mean, in a year, less than a year, we are planning for that. The payloads are under development. This will be going to L1 point. It's called Aditya L1, India's sun mission. And India also has major research facilities for astronomy. For example, the biggest radar in the frequency band of up to 50 to 1420 megahertz is in India. It's called Giant Meter Wave Radio Telescope in Pune, which is the dish is dish itself is of the order of 45-meter diameter. You have 30 of them, and covering a distance of 25 kilometers. Very precisely, you can, orient each one of them self-aligned. Very precisely. It's an engineering marvel. It is comprising of mechanical engineering, electronics engineering, civil engineering coming together, right? We have flown to moon. You already know that. And there are discovery class results. We were the first to discover water on Earth, and we were the first to discover water molecules on the atmosphere of moon. We say moon doesn't have an atmosphere. Moon has an atmosphere. It is extremely thin, extremely thin. The number of particles, number of molecules may be of the order of, per cc if you take, it may be of the order of 100 or 1000. It will not be like what you have here, but it exists. Okay, there's large amount, significant water molecules exist there. Doesn't mean that you will have, enough water to drink. That don't misunderstand that. There are a lot of, other research activities also done. And then we have Chandrayaan-2. Chandrayaan-2 is still orbiting, and it produced results. We were able to map the lunar atmosphere with that. And not only that, we were also able to map the lunar surface. The 3D view of, for example, Sarabhai crater there. There are several of such high-resolution imageries which we did with the Chandrayaan-2. And we had the Mars orbiter mission. The first attempt itself, it was succeeded. The first nation, to succeed in the very first attempt in Mars mission. And we again explored the atmosphere with a mass spectrometer. The atmospheric composition, how does it vary with altitude, in space, in time. And of course, there was Mars color camera. There were so many other payloads. I'm not going into the details. High resolution, 3-dimensional imaging of the system. You can see it here. And we have a classic mission for astronomy. It's called AstroSat. You may be knowing about Hubble telescope and now James Watt, so many things. But we have a mission which has produced the discovery class results. Its name is AstroSat. Okay, if you Google it, you will know what are the major findings made with that. So ISRO has state-of-the-art facilities for space and atmospheric research, and is a world leader in space research, especially in the tropical, middle, and upper atmosphere, ionosphere, magnetosphere system. And there is an evolution of satellite that was taking place from our INSAT 1A now to INSAT 3D, right? And there were a host of other payloads coming up. What should be our approach? Should it be ground-based observations? Should it be space-based observations? Should it be balloon-borne? Should it be only glaciers? No. You need to amalgamate all of them together. You need to have aircrafts. We have aircraft observations. We have balloons. We have ships making the observations. We have network over the land. We have satellites. All these data are to be put together, assimilated. We say assimilated together with a numerical model to know the weather, to predict the weather, and predict the climate. Okay, but satellite system alone will not do. You require proper ground-based system also. One of the most important thing here is analytical skills are required, not only in space research, in atmospheric, in climate research, in planetary sciences, in astronomy, everywhere. One of the thrust areas is going to be, you being engineers, I'm very specific about it. One is artificial intelligence and machine learning. Let me tell you, in the next decade, it's already there, it is already in place, but it is going to be much more dominated by artificial intelligence and machine learning. You already are getting the benefit of that, right? Big data analysis, satellite data inversion techniques, and improvements in numerical model and weather and climate forecast. Cutting across the discipline. It doesn't matter whether you are an electronics engineer or you're an electrical engineer or a physicist or a civil engineer. These are the thrust areas, especially artificial intelligence and machine learning and big data analysis. In space research, I am not talking about the information technology area, which is a different industrial domain. I'm not an expert either. So I thank you very much. I took a little bit more time. I'm very sorry that I took a little bit more time. Probably your dinner may be waiting. Thank you very much.
Thank you, sir, for such an informative and wonderful session. Now, participants can ask questions later to the session in the live chat, or you can put it up in the WhatsApp group. Your questions will be read out by our team.
No questions? There's a problem with the no questions. No questions means you understood everything what I told, or you did not understood anything what I told. Both are not correct. Correct?
Hello, sir.
Yeah.
We have a question from one of the viewers.
Yes.
Rahul Dev has a question regarding Aditya 1 mission.
Mm-hmm.
NASA has covered their Parker space probe by carbon composite. So how ISRO is going to overcome this challenge in order to withstand the high temperature, and it should also maintain a cool maintain a cool temperature in order to work the components of the payload in the solar probe. Or is ISRO borrowing the same technology as NASA itself to withstand the heat with materials like reflecting surface, gold-plated beryllium, etc.?
Actually, it's a very nice question. Firstly, it's a very nice question, and it's an important question. Let me tell you, firstly, we are not following anybody, or we are not following any nation. Like, for example, America has developed so much, Russia has developed so much. It is not that we are in competition with them. We are never in competition with them. The science which we are doing has its own value, whether it is in Aditya, whether it is in something else. We should also accept that the developed nations started the research on space decades before we started. And definitely there is a lag between the developing nations and developed nations. And definitely we cannot be in competition with them as far as we are concerned. We have our own targets for these things. That is the answer for the first part in a philosophical manner, the objective manner. Now coming to the Parker mission, yes, Parker mission is such an important mission that it can go, it is the first mission that it can go so near to the sun, means it can withstand such high temperature. The devices that you have can withstand such high temperature over a longer duration. Any device may be able to withstand for a shorter duration, for such a long duration. This is actually, you know, for your information, I'll tell you, the instrument, the components that is being flown in space is called space grade components. All components are to be radiation hardened. All temperature have to withstand very high temperatures of the order of typically 60 to 80 degrees centigrade, or very cold temperature of the order of maybe 10 degrees centigrade. Electronics still has to work. This is actually part of our, any space-borne system has to do that. Of course, our satellites will be having a thermal protection by itself. Mechanical engineers here will be knowing about that. We can actually, through heat transfer things, we can regulate the temperature to an extent. But Parker mission is a completely different thing. It is going so close to the sun that the temperature that Parker faces will be of the order of hundreds of degrees centigrade, much more than what we are facing. And the electronic devices which normally works will not be working. Okay. So currently we don't have that kind of a technology, let me tell you, to have something like Parker mission to go. But now coming to Aditya L1. Aditya L1, the point, it is a vintage point. It is far into the away from the Earth in the Sun-Earth axis at a point called L1 where the gravity of Earth and the Sun is equal. When you look at, you can still monitor the Sun without facing much temperature. You don't have to borrow the technology from somebody. You can still do that. Okay. So with your radiation hardened systems, you can still do the observations, and that is what is happening with Aditya L1. Aditya L1 will not go as close to the sun, as Parker did. Aditya L1 will be at L1 point, which is a few million kilometers from Earth. But that will have the sustenance with the radiation hardened systems. That's already there. The third part of this is, again, coming to, there are other technologies that are existing. For example, there are mechanisms by which you can devise techniques, device systems by which the radiation that is coming in will be reflected rather than getting absorbed. That is a point that he was trying to point out. That is a very good point. Of course, this is actually part of material research, material science research. And material science research with the advancement in India, this is going to come up. Let me tell you one thing here. material science research in India is not done by ISRO alone. Actually, there is a large chunk of research institutions in India which does material science research. We should know one thing very clearly. ISRO is not developing all the technologies from the component level to the development of spacecraft to launching and all those kind of things together. No, the devices are coming from standard sources. Most of the devices in the sense components kind of. Okay. Without that, how do you do that? And electronics engineers here knows how many foundries are there in India which can make advanced chips. We have to rely on people who are outside for certain things. And of course, Government of India has taken action towards this, that make in India and bring the industry, global industry to India or develop Indian industry with the Indian manpower so that the nation will be developing as such. And this is a policy matter that the government has taken a decision. It is in the correct direction. But at the same time, currently, if you ask all the components that is to be used in ISRO missions are coming from ISRO, no, sorry, no. It is coming from industry. It is coming even from abroad because some of the components we don't have. Why, for example, a simple example, the laptop that you use, what are the components that are made in India? So at such things, you have to rely on the world, the global market, right? But there are critical systems. Component will not make a rocket. Component will not make a laptop. Okay. So you have to design systems with that. Electronics engineers do that. Electrical engineers do that. The mechanical systems, the control systems, and your computer science people, doing the software part. So all these things are being done in ISRO, but not that from every brick in the sense from component level. Definitely, we have to rely on the globe or global leaders. And it may not be even often economical to have your own industry to develop for a chip. It is something like when you want to make a laptop, you don't go for, making a component factory. Rather, component factory will be maybe by Intel, maybe by somebody else. You will use the components. That will be more economical and more advancement also, because otherwise you need to have specialists in every domain, not one or two specialists. If that is the case, we could have competed with Intel. No, that is not possible. Okay, it's a good question. But at the end, let me tell you two things to make the answer very straight. We are not going to compete with any nation in the world. We have our own agenda. The agenda is very clear. The Indian agenda is very clear on our progress, on our natural resources, on our space assets, on our climate change, on our environmental monitoring, on our fundamental science. Number one. There, we are advancing at the maximum pace that is possible. And let me tell you, it is you people who will be coming up and taking the responsibilities from the current generation of people like me. Okay. So, and we were actually taking the responsibilities from our earlier generations. They did a fantastic job. And the benefits that we are reaping upon is based on the marvelous job done by our earlier generation. And the next generation is going to take on the job from the current generation. Number one. Two, Aditya L1 is going to monitor the sun at not as close proximity as Parker mission, but it is going to have its own components for space monitoring, including heliosphere and the energetic particles that are coming from the sun, emitted from the sun, and giving prediction well in advance to the Earth. Thank you. Next question.
Good evening, sir. So the next question is, sir, ISRO has achieved one of the greatest Mars mission, Mangalyaan. Its biggest peculiarity is its budget, only 75 crores. So the explanation given by ISRO is that they used a phenomenon called gravity to reach Mars. So, sir, shortly, could you explain how it works?
It's a very nice question. Actually, you require propulsion system for launching a satellite, which you already know. You have the huge chunk of the mass that is coming out, the propulsion, and then the rocket goes up. Now, once it is in a cruising phase, you can from an elliptical orbit. Actually, I showed in a figure earlier. You can have a long elliptical orbit, and further increase the elliptical orbit. Eccentricity of the orbit, further increase the eccentricity of the orbit, further increase, and finally it becomes long elliptical orbit, and then you can leave the Earth. When you are doing in an elliptical orbit, what you are doing is you are firing a small amount of fuel at a critical point. So your total velocity at the the point very near to the Earth increases, and that will be able to throw the satellite to very long distance, provided you are changing the orbit from smaller elliptical orbit to a longer elliptical orbit. This is actually taking the gravity, taking into advantage the gravity of Earth. Actually, you already know this. This is actually coming from your the Kepler equations and things like that. And second part is, while cruising, now you should aim for where the Mars is going to be when it is traveling the interplanetary area, and then capturing in the Venus also. Mars also is a very, very critical thing. Whether it is in the Mars or in the Moon, because you have a propulsion system, it is freely laying. It is not under the gravity of the Moon or under the gravity of the Mars. But if you go at a proper angle of attack, which require enormous precision, enormous understanding, enormous modeling of the propulsion systems and tracking, the trajectory analysis, then you will come to a point where this will be captured by the gravity of the planet. Otherwise, it will fly away, or it may nosedive into the planet. Both can happen. If your angle of attack is not proper, what will happen is it will fly away. Then you will not be there. You will not have another say to come back. The second is it may nosedive into the planet or the planetary body. Both should not be possible. So you require enormous modeling with this. Basically, gravity-assisted thing is what I told. Two things. One is the increasing the ellipticity of the orbit, and finally making it long elliptical orbit and then escaping. And second, by spending little bit fuel rather than directly going like an airplane with its own propulsion system at full. So for that, you have to make multiple revolutions around the Earth, and each time having the orbit rising of the the farthest point and then escaping. And second is the gravity capturing at the planet where you reach. Where you want to get captured, like whether it is Mars or Moon or any other planetary body. This is an enormous, precise calculation that is to be done, and ISRO has successfully completed in both Moon and the Mars mission. Yeah.
Okay, next question.
Good evening, sir. I'm Akshita. There is a question in the YouTube live chat box. What are the present viable applications of AI and ML in the area of space research, and what is more expected out of it in the future?
Excellent question. Firstly, you name it, it's a domain in artificial intelligence or machine learning. I'll tell you a very simple example. Very, very simple example. The amount of radiation coming from the sun is fixed. It's not varying drastically. What I'm saying is not extreme ultraviolet or gamma ray, which doesn't really affect the neutral atmosphere, but rather affect only the upper atmosphere. But our weather is changing continuously. June 1st every year, monsoon need not hit Kerala. So what is happening there? Actually, there is one way that you can model is numerical modeling of the atmosphere. One way that you can have is numerical modeling of the atmosphere, where you are not able to solve all the equations. Analytical equation means the equations are coupled. The fluid mechanical engineers will know it. There's something called a Navier-Stokes equation. The Navier-Stokes equations are for fluid motion and for the energy and continuity. When you solve it, you will not be able to solve it analytically. The reason being they are coupled. Coupled means, for example, velocity in one direction, say northward direction, will be affecting the velocity in the eastward direction. So if you want to derive the velocity in the eastward direction, you should know what is the velocity in the northward direction. At the same time, if you want to derive what is the velocity in the northward direction, you should know what is the velocity in the eastward direction. I'm telling in a very coupled, very, very simplistic manner. There are non-linear coupled equations. You cannot solve it analytically because the change in one affects the other, and the change in that affects this chicken egg problem. Okay, so you can solve only numerically. While doing numerical simulations, there is a problem. Any numerical simulation will diverge after some time. You will not be able to have a solution after some time. That is why weather prediction models, usually they will not be working well beyond probably a few days. Okay, There can be extended, there can be short range models up to around 4 or 5 days. There can be extended models up to around, say, 1 week or 15 days. Other models will fail. Why we cannot predict what is going to happen in the next 1 year, in the next June, what is going to happen? Can we predict? We do predict now. We have prediction now. It is based on statistical models. We do have. But we also have history of all the things which were happening in the last probably several decades. Can't we mine the data and make a model that will be suitable for forecasting either the weather or the climate? There's a difference between weather and climate, okay? That I'll come in 1 minute. But before that, let me complete this. There's an enormous scope, and people are thinking in this line. But so far, it is not successful. But it is, in principle, possible to predict the weather at any place or the climate of any region. Over weather means over next few days or maybe a month. Climate means over the next year or maybe decade or maybe centuries. What is required is artificial intelligence or neural network. This will be one of the applications straight away which comes to my domain. The second domain, which is not really my domain, but I am aware of being in ISRO, is, for example, you have the imageries which are high resolution imageries which are getting captured. Okay. How do you monitor the drifts which are happening? For example, Earth has, an earthquake kind of thing is happening. A small structural change has occurred on the Earth. How do you really make out from these two imageries really? Because the noise will be, the structural change that it has made when you look from space is such a peanut that it will be buried in noise. But how do you really make out? There are mechanisms by which you can make out the huge bulges that are produced by the earthquake or the impact that earthquake has produced. People are working on such things. Third aspect is we were talking about, for example, carbon dioxide. What happened during the last 100 years? What will happen in the next 100 years? Do we know? Can we forecast? Is there any way? There are ways and means, because there are certain background data and there are certain forces that are going to affect it, including economic forces and social forces. What is the kind of shift that is going to happen in future? The machine language will be able to tell you. Okay. That is the place where your artificial intelligence is going to be one of the, I'm talking about Earth atmosphere system primarily. It is also applicable for any of the systems, even for your analysis of the systems, in any domain. Let it be, for example, error propagation analysis. Simple example. Error propagation analysis for a circuit which an electronics engineer has designed. A complex circuit has been designed. What is the kind of error propagation possibilities? What is the possibility for failure at each of those components? Each of component, in the sense, each of the level of the circuit, which is not a very straightforward circuit, it's a complicated circuit. A straightforward analysis may not be possible with it. Artificial intelligence will be able to do that. The simplest thing is you already know that most of the robots which you are driving is already running in artificial intelligence. People started already using. It is a common practice now in several advanced countries that instead of having a domestic help, they will have cleaning from robots, or in future it is also going to happen that robots will be your companions. So how do they learn things? How do they understand your language? It is already known. You just search in Google, two of your friends together, you search for the same keyword in Google, you will get 2 different results. How is it possible? It's possible because they have already employed artificial intelligence and they know what is the taste of A, what is the taste of B. You will get 2 different results for the same keyword which you are searching. So artificial intelligence is coming in remote sensing, data remote sensing, which I told you, high resolution remote sensing, urban planning. So many places this is going to happen. Of course, at national security level also it is going to happen. So you name it, you can have artificial intelligence and machine learning in any area. Let it be robotics, let it be atmospheric science, let it be economics, let it be economics, let it be. I will tell you another simple example. Mayan civilizations. Mayan civilization is already gone over in South America. The archaeology can be done from space. But how do they do that from space? How do they find out that there is a structure that existed actually, which is buried in the trees or the boulders and things like that? There are mechanisms by which you will be able to do it, image analysis, and then applying artificial intelligence. It's possible. It is possible in any area. I named only a few. You will be able to, you may be knowing much better. In addition to what the software companies are doing. Of course, there are other routine things for data mining and things like that. Okay.
Okay, let's move on
So
to the
we
next.
have another question.
Yeah, go ahead.
Sir, after BTech, can I join as scientist engineer SC post in VSSC through ISRO test?
Yeah, that's a very good question. Actually, I wanted to tell you, in fact, Vinayak was yesterday pointing to me that people will be also interested in this one. Let me tell you this. ISRO, as I told you, is an ocean. You name it, we have the specialty. Okay, right from any domain which you can think of, either in MBCET or outside. So a BTech fellow in any discipline, in principle, can join us. Let me tell you what is the procedure by which you can join. As a BTech fellow, there is a national entrance test. It is not called a national entrance test, but a national test. We get lakhs of applications for a post when it is advertised. The number of posts may be 50, but you will get maybe 3 or 4 lakhs of applicants, maybe 2 lakhs, and all very qualified people. You should know that. Now, how do you select them? You cannot screen them based on interview. It is impossible. You cannot screen them on the basis of mark, because Kerala University mark will be different from Calcutta University, will be different from Delhi University, will be different from IIT. So you cannot have a normalization for that. So what is possible is conduct a national level test with the same question papers. All people attending. This you know already. You have already passed the qualifying exams. So this national level test you have to qualify. Qualify means for each post they will. It is not like GATE that you qualify. It is not like that. But rather, suppose you have some X number of vacancies, they will call for each vacancy. Maybe they will call 10 people for interview. Just I'm telling an example. It need not be necessarily 10. It can be maybe 6. It can be maybe 10, depending on the number of requirement for each. Okay. So those people will be called for interview. And this written test, first thing is written test. You already know. Actually, questions are already available for the past question papers are already available. So you already know what is the kind of question papers questions that will be asked in each domain. All right. People are actually training parallelly, not only for ISRO, for other people also. In fact, that comes parallelly with your GATE preparation. Okay. So your GATE preparation and ISRO preparation or some other agency also, you can prepare like that. And then you have to qualify this. Qualify means you have to be in the top. And let me tell you, even if you are not getting through in the very first time, you don't get disappointed. It doesn't mean that you are not qualified. All what it means is you are not lucky. The reason is, you just imagine 1 lakh people attending the same question paper, and one question by one small mistake can bring your rank by probably of the order of maybe 100 or maybe 1,000 among the top itself. Okay. So don't worry about that. Maybe in the first attempt, maybe second attempt, you will be able to get through. You are only 21 years, so maybe in the first or second attempt, you will still be having maybe 22, 23 years. So you qualify in the written test. Written test is fully technical. Fully technical. It's not like a civil service and all. It's fully technical, like your GATE. And then you come for interview. And in the interview, it is full again technical. And any place where you are facing an interview, let it be ISRO, let it be any place. One of the fundamental thing in ISRO is you should not mug up anything. You should not mug up anything and then reproduce. You should understand from the core. Any interview board, any successful interview board, for that I can bet ISRO is a master. Okay, our people are masters in that. They start from the very fundamentals and build upon. And build upon. Build upon means your level will be going up from question to question to question. Okay, and they will really find out which is your limit. They will really find out which is your limit. From the very fundamentals to your concepts, to your applications, to your capability in different domains, and then they will be able to grade you where you are fitting in. Exactly, they will be able to do that. All right, that is what the expertise we have. It will not be by one person. There is a committee. That committee comprises of domain special people. Okay, in addition to a few general core committee. So they will be able to clearly judge you, and all what is looking for is your technical capability, your understanding, your fundamentals. So that's why I'm telling you, when you are talking about a system, don't mug up. You try to understand what is the physical principle behind it, what is the process by which you do. Why, for example, when you are designing a circuit, what is the basic principles that you have to follow? Let it be a simple amplifier. Okay, let it be a very simple amplifier. How do you design an amplifier? Then they will go to say, how do you now make it a high power amplifier? How do you dissipate the heat? How do you account for the heat dissipation? You understand? So you will be able to you will be able to know. They will be able to know where is your level, either in electrical or electronics or mechanical. Mechanical, same thing. Same thing can happen. Structural analysis, for example. Civil engineers have very good scope in structural analysis. We have civil engineers and mechanical engineers in our structural entity, and same is the case with aero. Okay, mechanical engineers, they do wonderful job, right? And electronics, civil, computer science. Computer science people are also required. Again, it depends on the domain. For example, you are required for algorithm developments, inversion developments, even for the remote sensing applications. Variety of areas where computer science people are required. So you name the domain, industrial engineering, for example, fire, fire and safety, production engineering. So there are various domains for BTech people. But of course, the most important thing will be definitely electronics, mechanical, chemical. Okay, definitely electronics, mechanical, electrical. These are the core domains. Of course, civil also will be there. Civil, in addition to this, we have our civil wing. But that is, we also have the real, the research kind of thing also. That is the structural analysis and things like that, right? The second way is go for higher degrees, go for MTech. But you should be, there you should be clear about which is the area which you are selecting, because not that all areas will be of use. Of equally, demanding. Okay. For example, RF design, VLSI design, there will be some requirement at that time, then it will be propping up. But BTech is one place where it can be very good because the intake is quite high for the BTech. All domains have possibilities for things. And what you have to do is you have to prepare well for your gate, and parallelly, almost the same thing will be useful for ISRO also. The difference is interview. Subsequent interview, I told you how to go ahead with your interview. There is nothing called an interview preparation. Actually, interview preparation come right from today when you are studying itself. Your basic concept. The concepts are important. The real practical applications are important. Why did you do that is very important rather than you did it, because doing can be done by duplicating. But a new design, an engineer, by definition, an engineer is a person who designs, right? So you should be able to design. And design means when you are able to do something small, you will be able to do big also from the first principles. That's applicable not only in ISRO, in any R&D organization. That is important. So your preparation here will be sufficient for the other agencies also. Except for, of course, there are some places where industry goes, there they may not ask you these kind of questions. There, of course, it will be different. Industrial applications. That I am not an expert. Okay.
So our next question is, as asked by Manisha Sharma. She has asked how soil moisture is detected and how can space research help in climate change issues?
Excellent question. Soil moisture, firstly, soil moisture is the amount of soil in the moisture. Okay. Now you have an electromagnetic radiation that is in the microwave. Microwave means you have, centimeters wavelength. Okay, or millimeter wavelength. The response of the, you have a space-borne radar, or you have a ground-based, you have an emission that is going to space in certain wavelengths, will be affected by the amount of moisture available at the surface. Because Water can absorb. For a dry soil where water is not there, for the same temperature, the amount of radiation in the microwave, in certain bands of the microwave, it will not be in all microwave domain, where water vapor absorption is very significant, you will get a different signature compared to dry soil. So it is a signature of the the microwave radiation that is reaching back the satellite, either through emission or when you are using a radar kind of thing. Both are possible. In that wavelength domain, what is the spectral response? Is the one which will be able to, with which you will be able to estimate how much is the soil moisture, that is the water content in the soil. For that, we cannot use a single frequency, because you need to know what is the soil temperature. Because I told you, for the same soil temperature, you can have different radiances reaching there based on the soil properties, or even soil texture, soil reflectance. So there are other parameters also you have to monitor together. Then in this particular wavelength, then what is the kind of response? Because other inputs come from the other wavelengths, like soil temperature can be derived from IR or from infrared radiation or from microwave. Okay, preferably from infrared radiation. Okay. So with that, you will be able to derive soil moisture. Now the second part of the question was what? Vinayak, what was the second part?
So about climate change. How can space research help in climate change?
Climate change. Excellent. The climate is changing, but climate itself means that it is not day to day. It is not from yesterday to tomorrow. It is over the last decade. So the question is very correct, because how long these satellite systems were existing? Yes, true. Satellite systems for continuous monitoring started in the 50s. But in a more advanced way, in a more regular way, it came up in the 70s. From the late 70s till today, we have the complete map of the globe at various spatial domains. That is fine. The spatial domain, spatial resolution can be different. Today, you may be able to get at meter resolution. That time, meter resolution will not be there. That is fine. When you cover the whole globe, at 1 kilometer is sufficient to map the clouds. When you are covering the whole globe, you have data from late 70s, 80, 90, 100, 2000, 2010, 2020, 50 years data already existing over the entire globe. You can find out the trend. What happened to the clouds? What happened to the geomorphology? Geomorphology means surface reflectance. Your urbanization. Urban cities were coming up. In an image I have already shown you. You can find out what is the difference between what happened, what was the prevailing situation in the late 70s to 2010 or 2020. You can also assess from 70s to 80s what was the rate of change, and 80s to 90s what was the rate of change, and 90s to probably now what is the rate of change. You'll find that now it is abruptly increasing. So they will be applicable they will be able to monitor the climate, because climate means, I forgot to tell you, in an earlier question I was telling you, I will define what is climate and what is weather. Climate means it is a long-term average. Long-term average. For example, today is 7th. Now it is about 9 o'clock. At 9 o'clock at Mar Baselius College, this should be the temperature on June 7th. This is what we expect on every year. Expected. Because you will average the value for 9 o'clock on June 7th for last 30 years. So this is what you expect. In the noontime, temperature will be different. So you will get, this is what is expected. This is called climate. A 30-year average of a system is called climate. Weather is not that. So I told you, this is the value which we expected Mar Baselius College today. But what is it that we have it today? There is a higher temperature or a lower temperature. There is more precipitation, lesser precipitation. There is more wind or lesser wind. All kinds of meteorological parameters can be different from what we expect. What is really happening now is weather. What is happening now is weather. What is expected is climate. Expected means expected based on the observations made during the last 30 years. All right. Now, satellites cover more than 30 years, multiple decades. So you'll be able to find the changes that were taking place in geomorphology, land use change, irrigation, river or water body changes, albedo, clouds, ocean water temperature. Temperature can be monitored from the space by infrared radiation. I told you, so sea surface temperature. So then you will be able to assess how much is the climate changing. But you will not be able to assess what happened 1 million years before from the satellite. Definitely not. So that paleoclimatic thing you will not be able to do. but you will be able to do from now onwards. Maybe around late 70s onwards, what is happening. And let me also tell you, maximum change in climate is happening from around late 60s onwards. So most of the latest changes satellite will be able to cover. So that is how it helps in climate change assessment. Yeah.
So due to time constraint, we couldn't take the rest of the questions. We're just ending up the Q&A session now. Thank you so much, sir, for answering all those questions with much vigor. Thank you.
But before I stop, I would like to thank the Honorable Principal, Deepak sir, Vinayak sir, and all the respected teachers who were responsible for conducting this and giving me an opportunity to interact with you. I really cherish it, and I'm very thankful to you for your patience. I took almost 2 hours of you, but that is fine. I enjoyed it. I don't know what about you. Thank you.
Thank you, sir. I now call upon Dr. Deepak G. Dilip, Faculty Advisor, ISTE MBCET, Student Chapter, for the vote of thanks. Sir, please.
Good evening, all. I'm Deepak G. Dilip, the Faculty Advisor of ISTE MBCET Student Chapter. I am entrusted with giving the vote of thanks for the event. First, I would like to thank our renowned speaker, Dr. K Rajiv, who accepted our invitation and took time from his extremely busy schedule to give such a wonderful and informative session on some very, very relevant topics in today's society. And sir, I have listened to many technical talk, but today's talk was like listening to a walking encyclopedia, and we are very much thankful for the way you took time and the enthusiasm you showed in answering to questions even after 2 hours of taking lecture after coming from office. So
I'm still in the office.
Oh, you are still in the office. Oh my God, sir, that's so we are actually very much thankful for you. So that the dedication you are showing is something that everyone should actually look upon. And sir, as a token of our appreciation, since we don't have a media to give it to you in person, we have prepared an e-memento. The students have prepared a e-memento, and it's being shared by to sir in e-memento. Please kindly accept this as a token of our gratitude. And moving on, next I would like to thank our dearest principal, Dr. Abraham T. Matthew, who joined us late this evening and still is still with us listening to the entire session. Thank you very much, sir, for your support in organizing such events and talks. Next, I would like to express my gratitude to Mr. Bobbin Saji George, Faculty Advisor, ASME MBCET Chapter, and the students of ASME MBCET Chapter for the support extended in conducting the event. I would like to thank Dr. Nidhi MP, Ms. Soumya, and all the faculty members for the support they have given. Finally, this event wouldn't have been possible without the students. I would like to thank all the students of ISTE MBCET Student Chapter, the Exicom, led wonderfully by Akshita. I would like to specially thank Vinayak, Rachana, Rohan, Ritika, and all for the wonderful way the event was conducted seamlessly. And finally, I would like to express my gratitude to all the participants who, I mean, we have around 600 registration, and even till around 9, we have more than 100 participants in YouTube. The people are more than 100 viewers are there. It was around 300 to 400. It was varying, but it's a very good number for a session which happened, and that shows how much interesting the talk was. And thank you again, sir. If you have nothing more to add, I think we shall wind up.
Yeah.
Thank you very much.
Thank
sir.
you very much.
Thank you, sir. Thank you very much. Okay, sir. Thank you. Let's wind up. Principal, sir, shall we wind up?
Yes. Thank you, sir. Thank you very much.
Thank you, sir. Thank you very much.
Meet again now.
Okay. Sure.
We'll see again.
Sure,
Thank you.
Thank you, sir. Okay. So we shall wind up the session. Thank you. Thank you very much, sir.
I would like to sit now.
Yeah, sure, sir.